Hello, everybody. My name is Gage Avonce. I am a student at Columbus State Community College. I'm going into my second year, and I will be talking to you guys about quick fatigue life characterization and how I use Python to do the data analysis for that. So on this first page here, the first picture you see is a zoom and close up on a stress strain curve for the disks that we use in our resistive magnets. The second is a strain amplitude or a strain data graph, sorry. The third is a strain amplitude graph. And then the last picture here is a screenshot of my Python program. So all the disks that we use for our resistive magnets have a fatigue lifetime. To find this lifetime, we must test the disks to find their strain range. Once we know their strain range, we look for an increase in the range out of your normal increase. And when we find that drastic increase in range, we know that tells us when the component will expire and therefore must be replaced. This process of collecting the data from these tests can have upwards of over 150,000 input results. So it's just completely unpractical to do by, hand or on the computer, either way, with your brain, just using an Excel sheet program and moving it. That's why my mentor, Rong Mei, tasked me with coming up with a program to help find the peaks and valleys in this data graph in order to be able to find that strain range. So this center picture here shows the disk materials, and the second picture shows the picture to the right of it shows the disks that we use. Now that disk right there is a copper or zirconium disk. The fatigue generated by turning the current on and off is analogous to plasticity of materials. This can be visualized as stretching of the material. So in order to get through all this data, I used Python, and I chose Python because it is known for being good for data analysis, and it's also a complex language, and a higher level language. So for someone who has less coding experience, though that may sound like it would be more, actually easier to use because it functions closer to English. When I first came here at the beginning, I had done zero coding work, never done anything with coding at all. And so I had to start from scratch and a lot of YouTube. But through that, I was able to figure out a lot of what I needed to do. And with our methods, I ended up using SciPy, which is a program for Python that helps with optimization, numerical integration, and things along that nature. It's a good data analysis tool. One problem I ran into when coding for this program was my arrays were of different size. And doing some research into this, I found out this is a common problem in real life data because it's not always perfect. You can have missing values in certain places, or your values may not exactly align equally. So what I was able to do to circumnavigate that problem was padding the arrays with NaN values or not a number values that was able to make it so that they were of equal length and the program would run correctly. There were quite a few bugs and such working my way through this program here. So it was a lot of trial and error. Yeah, a lot of trial and error. I was able to get it to output to an Excel sheet and have it create its own Excel sheet, and you can go in there and actually change the path to whatever you would want it to be, which is nice. As well as as you can see, if you if you can look in there and see all the green text is it's not functional code, it's an explanation for the program, and it also says like where you can change things for like change your file path for whatever different file you're using, or so on and so forth. So that way it's easier to use for someone who has not used Python or can't just look at code and know what's going on. That way they have something they can read. For the sorry, I don't know why this is there. For the what is going on? For the results, sorry. Improved data processing of magnet sheets. So the entire point of this task was to make it so that way my mentor would have to spend significantly less time working through this data. As before, they had no program for this, and you would have to run through the data manually. And a benefit of reducing that time and increasing the efficiency is labor cost. Labor cost is huge for all companies, whether it or even government laboratories for funding. No sense in wasting money. Another benefit of this program is it shows the cycle where the component begins to break down and needs replaced, which allows you to perform preventative maintenance. Because if you do not perform preventative maintenance and you don't know when the component breaks, well, if the component breaks, it could also lead to something else breaking. And so now you have a compounding issue. The test range for figure 1 was between 44 to 445 megapascal, and that is our stress strain curve. And that's just the pressure at this, that was the pressure at this stress level. We found out that the disks last around 5,000 cycles of on and off power distribution. Figure 2 is a closer look at that stress strain curve, basically zoomed in with less data. So that way, if you look at the first one, it's really kind of hard to see, the lines blend together. But this way you can see more up close of what's going on. You can see the looping action that's actually happening there. If you were to extract that into 3D, it would look almost like a spring or a coil. The next figure in the bottom left is the strain and amplitude close look. And then the figure 4 is that strain amplitude range. And using the process data, that is actually what we got using the program. And as you can see where the arrow points and the range is going drastically up, that is where it fails. That is the failure point. That's where you would want to replace your component, your disk. And so to find that strain range, that's why we needed to find the peaks and valleys of the strain, because the strain range is just delta strain. Delta strain equals strain 1 minus strain 2, right? Your peak minus your valley. In conclusion, this program is important and useful because it can process a high quantity of data quickly. I believe once I pressed the button, it took maybe 15 seconds for it to output the new Excel sheet, compared to the days or weeks it would take a team of people to go through 154,000 inputs to find all the peaks and valleys in them. As well as we already mentioned how it can reduce labor costs and improve people's efficiency in the workplace. Ways that I can improve the program, I can improve it by correlating the cycle number to the peak and the valley, so that the way the location can be located easier. Because right now you can go and you can look at the peak and the valley in the Excel sheet that the program outputs, but then you have to go back into the original Excel sheet and correlate that with the cycle number in the original sheet. So it's a little more work, so that it could still be optimized and become more efficient. As well as we noticed that there was a bug in the programming where you would get weird weird values, in the sense of if you would look at the graph, you would have your normal curve, but then you would have outliers that were just like at zero for no reason. And so that would be something that going into the code and trying to figure out what exactly is causing that and how we can fix that and remove that and make it look more appealing. Because that wouldn't be something that would necessarily affect the functionality because you know that's not part of your data, but it definitely can look wrong and could be confusing for someone who doesn't know what they're looking at. I believe that is all I have for you today. Thank you so much for your time.